We'll start with section 5.2 in this lecture. We'll learn about the definite integrals. So here is a formula to calculate the definite integral, integration a to b f of x dx. So in the last section, we did learn that area under the curve, which is integral a to b f of x dx, we did calculate using by summing the area of the rectangle, the length times the width, assuming we have n rectangles. So we bring this limiting condition in approaching infinity, which can compare to the area under the curve, which is like you have an infinite rectangle and you're summing up. So again, I want you to read this as area under the curve, which is integration a to b f of x dx, which is given by the sum of f of xi times delta x, the length times the width of the rectangle. So we have a nice name for this sum. We call it as a Riemann sum. And he is a German mathematician, Riemann, in the year between 1826 to 1866. He was the one to find this Riemann sum. So first, let's write the integral notation and let me explain you each of these variables. Integration f of x dx with the limits a to b. When I have a limit for this integration ab, I call these type of integration as a definite integral. And this dx is called as the variable of integration. And the function what I integrate is called as integrand. And a is the lower limit and b is the upper limit. So let's do this first example. You are given a function, you are asked to calculate the Riemann sum with n equal to 6. This is similar to your section 5.1. Other than that, you're naming the summation function as a Riemann sum. So let's graph this function x squared negative 2x. It's a shifted parabola. It's an open upward parabola. So let me draw this. Or let me draw even an extended one. So first let me write the function f of x, which is x squared minus 2x. You're given a is 0, b is 3, and you're also given n is 6 because you want 6 rectangles. So let's calculate delta x using all these three values. And we have 3 divided by 6, which is 1/2. So I'm going to name these sample points. So let me name these sample points x sub 1, 1/2, x sub 2, 1, x sub 3, 3/2, x sub 4 is 2, x sub 5 is 5/2, x sub 6 will be the last point, which is 6. I'm using the rightmost, it's 3 rightmost endpoints. So this is our step 1. So let me name all these points on the graph. This is 0, 1/2, 1, and then you have 3/2, 2, 5/2, 3. So name these points as x sub 1, x sub 2, 3, 4, 5, and 6. You're using the rightmost endpoint, so start drawing the rectangles from the right. Draw a vertical line towards 3, vertical line towards this 5/2. Extend this to make it look like a rectangle. Draw a vertical line from 2, joining the curve, and again you're seeing an overestimate. For this one, you again draw a horizontal line and then you see an overestimate. For the next one, you draw a vertical line, horizontal line, you see an underestimate. For the next, again you're seeing an underestimate. It's a decreasing graph or a decreasing function. For the next, again you're seeing an underestimate because it's a decreasing graph. So once you draw these rectangles, you're good to calculate the Riemann sum, which is summation I equal to 1 to n is 6 here, delta x f of xi. F of xi are called as the sample points. So you know how to expand this summation. It's delta x, f of x1, f of x2, all the way up to f of x6. So plug in these functional values, simplify, and you see that you get 7 over 8. So this is the area under the given curve. Next, we want to calculate the integral g from -3 to 3 for the graph given below using right endpoint, left endpoint, and midpoint. So this is basically reading the graph problem. So you are not given an explicit algebraic expression for g, but you are given a graph of g. So using the right endpoints. So first I want you to come up with an expression for delta x using the right endpoints. So do write down right endpoints. Then you write delta x equals 6 is the rightmost point. So here you are given -3 to 3, the limit values with 6 as the subintervals. So in the graph you have given it as a and a. I want you to mark the first a on the x-axis as 2. So the second point becomes 4. This one is 2. So this is 4. And the last one is 6. Similarly, we have -2, -4, -6. And this is 2 here on the positive y-axis. So start by writing the delta x value, which is 6. -6 divided by 6. I want you to change the limits here as -6 and 6. So this is 12 divided by 6, which is 2, which shows that like why we divided the intervals with a width 2. So name these points as x sub 1 because you're using the rightmost point, x sub 2, x sub 3 is 0, x sub 4, x sub 5, x sub 6. So write x1 -4, x2 -2, x3 0, x4 2, x5 4, and x6 6. So we have -6 to 6, g of x dx. Expand using the formula gx1, gx2, all the way up to gxn. So we have 2 and the gx1 is 2. So this is reading the graph. You read g at -4. From the graph it is 2. That's this point. Similarly, calculate the values from the graph. It's -1, -3, -3, -1, and +5. So simplify, you get this expression as -2. Similarly, do a calculation for the left-hand points. And you see that you get the answer as -4. Try this with the midpoints. And you get the answer to be -7. The next one, you're given a table of values of an increasing function f. And using this value, you will come up with a lower and an upper estimate for the integration. So name these x values as x sub 1, 2, all the way up to 6. And you understand that f is an increasing function here. So the question is asking you, use the table to find the lower and the upper estimate, which means this is the integration given in the problem. The upper estimate is bounded by r sub n and the lower estimate is bounded by L sub n. This is the lower estimate and this is the upper estimate. So first let's calculate the upper estimate. Having been given that the delta x is x2 minus x1, which is 14 minus 10, which is 4, we calculate the upper estimate, which is r sub n delta x. F of x2, you choose the rightmost point, so you leave out 10. fx3, fx4, fx5, fx6. So this is 4, -6, -2, -1, 3, and 8. Simplify, you get 16. Similarly, do a lower estimate calculation with the left endpoints, leave out the rightmost point, and you see that you get a lower estimate L sub n, which is -64. So now you can plug in these expressions and you can say -64 is bounded below by this integral So let me go back and rewrite here for the integration that the lower estimate is -64 and the upper estimate is 16. One more example, the midpoint rule, which we already saw in the previous section, but we are seeing with the Riemann sum. So you want to use this midpoint rule where when you calculate delta x, it's the same formula b minus a divided by n, but when you calculate the functional values x1 bar, x2 bar, you use xi minus 1 plus xi divided by 2. Suppose I have 1 and 2. The midpoint will be 1 plus 2 divided by 2, which is 1.5. So we will use this midpoint rule to approximate this integral here. So sometimes when the curve is this messy, without a calculator, you might not want to draw this graph, or even the graph is not needed for any other problem. All you have to make a note is you have to bring down a number line. Just a number line is sufficient. Draw the left extremity 2, draw the right extremity 10. And you are given n equal to 4, which means 4 rectangles. So break this as 4 rectangles. So mark this unit as 4, 6, 8. So you want to use the midpoint here. Midpoint means this is x1 bar, x2 bar, x3 bar, x4 bar. So you have these to be the midpoints. Calculate 2 plus 4 divided by 2. 6 divided by 2 is 3. Similarly, this is 5, this is 7, and the last one is 9. So you know the function f of x is square root x cube plus 1. You know a, you know b, a is 2, b is 10, and you know n 4. You also know delta x is 2. So use all these values in the formula. It's 2 to 10 square root x cube plus 1 dx. So it's delta x f of x1 bar plus f of x2 bar plus f of x3 bar plus f of x4 bar. So delta x value is 2. Then you calculate this is f3, f5, f7. You plug in all these x sub values plus f9. Now simplify, you get this to be 124.1644. Each time when you calculate the functional value, you can use this square root x cube plus 1. So here we have some properties of definite integral. Integration a to b f of x dx is same as integration negative b to a f of x dx. So suppose you're integrating 2 to 5 x dx, you can say that this is same as integration negative 5 to 2 x dx. Properties are really important when you calculate definite integral. This will save a lot of your calculation time. What suppose you have sine of the function 100,000. The limit is negative 2 to 2. Or sorry, negative 2 to negative 2. You see the lower limit and the upper limit are the same. So you really don't have to evaluate this integral. All you can say is integration is 0. Similarly, integration of a constant moves outside, it's cb minus a. When you have integration of functional values, you have to distribute the integral to each of them. Constant moves outside. Distribute the integral to both of them. And the last one, suppose I can split this number line as a to b and c. When you add this integral value from a to c and integral value from c to b, all you get is the integral on the entire length, which is a to b. That's what this formula says. A to b and c to b, sorry, a to c and c to b, sum up, you get a to b. So let's do this graph problem. You are given a graph G consisting of two straight lines. You're seeing a straight line 1 here and a straight line 2 here. And you're seeing a semicircle here. So you have 3 p's of the curve. Use this graph to evaluate the integral. Before even I use this graph, let me mark this graph, identifying it as a triangle here in this part, and again a triangle here. And you understand the middle one is a semicircle with the radius as 2 because this is your point 40. And when you read this, understand this is positive x-axis and the positive y-axis, negative y-axis. So now, let me mark this point as 6 and 7. And if you see area of this triangle, you can say the length is 2, the height is 4. So when I calculate the area, 2 times 4, I get the answer is 4. Similarly, when I calculate this area, it's 1/2. Base is 1, height is 1, so the answer is 1/2. When I calculate the area of the semicircle, it's pi r square divided by 2, r is 2, so it's pi times 4 divided by 2, so we understand it's 2 pi. So now let's do this. 0 to 2 gx dx. So all you do is, when you read 0 to 2 gx dx, you see it's the area 1, which is the area of triangle. The base is 2 and the height is 4. We just calculated it is 4. 2 to 6. Read 2 to 6 carefully and you see the curve is below the x-axis. So you say that this is the negative area of semicircle. And you read that this is your shaded region 3 from the graph. So we already calculated it's pi r square over 2, which is 2 pi, but with a negative sign, this becomes negative 2 pi. Now we want to do 0 to 7, which means you are summing up 0 to 2 on the x-axis, plus 2 to 6 on the x-axis, plus 6 to 7 on the x-axis. So integral 0 to 2 is your part 1 of the problem, A. 2 to 6 is your part 2 of the problem, so you don't have to recalculate, just bring down the answer from the top. And the third one is your part 3, shaded region 3, which we calculated that the area of the triangle is 1. So sum it up. So all you have is 4 plus 1/2, which is 9/2 negative 2 pi. So this is one way of calculating area under the curve using the geometrical figure, which looks like a nice rectangle or a triangle or a semicircle. The next problem, evaluate the integral by interpreting it in the term of negative 3 to 5 6 minus 2x dx. So first let's draw the 6 minus 2x graph, which is a straight line. So mark this point, let me redraw it. This is 3, it's negative 3 to 5. And this width is 2. So draw a straight line. This height is 4 and this height is 12. And this point is negative 4. I'm going to mark this shaded region as 1 and mark this shaded region as 2. So this negative 3 to 5, 6 minus 2x can be divided into two parts. One is negative 3 to 3, 6 minus 2x, and the other one is 3 to 5, 6 minus 2x. So this is 1 half 6 times 12, negative 1 half 2 times 4, area of each of these triangles, 1 and 2, shaded region. Simplify, you see that you get 32. So first come up with drawing this line 6 minus 2x to make sure where it cuts the x-axis and the y-axis. And then you will be able to figure out that you have two triangles, 1 and 2, and you know how to calculate the area of a triangle, which is half times base times height. In the next example, you are given two limits and you are asked to calculate limit 1 to 4. So first draw a number line from 1 to 5, which is the longest interval here. 1 to 5, the answer is given, this integration value is 10. 4 to 5 integration value is 5.9. The question is, what is the integration value from 1 to 4? So you write 1 to 5 integral can be written as 1 to 4 plus 4 to 5 integral. And when you write the integral, make sure you write it's the integral of the function f, and the variable of the integration is dx. So you have to write the variable of the integration also. So 4 to 5 is given, in this place plug in 5.9. 1 to 4 is not given, put question mark, and then 1 to 5 is given 10. So in this linear equation you have only one unknown. You can say 1 to 4 integration is 4.1. In the next example, 0 to 4 f of x ds, if the function 2x, 2 for x less than 2, x for x greater than or equal to 2. So mark 2 here on the x-axis. So for less than 2, you have a straight line which is 2. And for greater than 2, you have a slant line with a height 4. So extend this to make it look as a height 2 and 2, and the total height is 4. So when you calculate, you can calculate this as the area of a rectangle, and then you can calculate this as area of a triangle. So you have two shaded regions here. So you can write 0 to 4 f of x dx is area of rectangle plus area of triangle. Area of rectangle is 4 times 2 and area of triangle is half times base times height. So this is 8 plus 2, which is 10 square units. So in this section 5.2, we learned about this Riemann integral, where we have this nice geometrical figures and we know the name of the geometrical figures to calculate the area. Or you can also say that the summation, we are going to define it as I equal to 1 to n, and then this limiting value, which is the area of the, which is the integration a to b f of x dx, which is also area under the curve. So all these are equivalent definitions which we learned in this section 5.2. So we'll end this section here.